Hello everybody. Today we're doing a review. I'm calling this review number 3, and it is a review of unit number 3, Functions and Transformations. If you are watching this and trying to review your math, I'm proud of you that you're doing this and you want to do well on your exam. Just a reminder that watching math is not enough. You need to do exercises yourself. In addition to this review package with the video reviews, you will get another review package. Make sure you can do all those questions by yourself on your own. Another good way to study, and what you should do as well, is redo all your tests. And and then you should be in pretty good shape for the final exam. Let's start out with the function definition. What is a function? Well, a function is a special type of relation where each value in the domain has one and only one value in the range. So in other words, every x value has only one y value. If one x value has two y values, it is not a function. So how do we determine whether a relation is a function? Well, it depends how that relation is presented to you. If it's presented to you as an ordered pair, right, as a set of ordered pairs, if any x value repeats, it is not a function. Okay, because if it's repeating, then one x value will have two different y values. If your function is presented as a graph, what you can do is what we call the vertical line test. If you draw a vertical line on any point on the graph, and if it hits your graph twice, then it's not a function. 3, if your function is presented to you as an equation, well, we sub in the x values, You can try 1 or 2, and see how many y values you get. So, if for every x value you sub in, you can do that mentally in your, when you see when you're given the function. If you sub in an x value and you get only one y value, then it is a function. If you sub in an x value and you get two y values, then it's not a function. So for example, if we're given a set of ordered pairs, such as -1, 3, -1, 5, let's see, let's just 7, 10, and 13, 4. Well, let's take a look at that. Oh, notice there is an x value repeating here. So an x value of -1 has not only a y value of 3, but it also has a y value of 5. So therefore it is not a function. 2. What if our function or relation is, what if our relation is given to us as a graph? Well, what if we're given a circle? Okay, notice if I were to draw a vertical line, see how this vertical line hits this relation twice? So this relation is not a function, because for this particular x value, whatever that may be, we have two y values. So this, it does not pass the vertical line test. Therefore, this is not a function. Okay, remove that pen. Well, let's try number 3. Let's try the equation of a circle. You probably already know it's not a function because you know what a circle looks like, and graphically it would not pass the vertical line test, so we know it's not a function. This relation is not a function. So if we were to use this test, sub in x values, see how many y values you get. Well, let's see. I'm going to sub in 0. Let x be 0. Notice when x is 0, I get 0 squared plus y squared equals 9. Notice I get y squared equals 9. So y equals the square root, take the square root of both sides. Always remember what you do to the left side, you do to the right side. Y is equal to plus or minus 3. So notice when x is 0, y could be negative 3. When x is 0, y could be positive 3. That means we have 2 y values for one x value, therefore not a function. Okay? There you go. I'm going to put this back up so you can see the whole page. Domain and range. Okay, domain. What is a domain? Well, domain is the set of all values for which x is allowed to be. Normally we present a function with x values being range and x values representing the domain and y values representing the range. So domain is the set of all values for which x is allowed to be. Okay, and range is the set of all values for which y is allowed to be. Uh-oh. There we go. So let's take a look at this. Remember, we cannot take the square root of a negative number. We're going to find the domain and range of each of these relations, and all of them are functions because you recognize this is the square root function, the reciprocal function, and the absolute value function. So they're all functions. Let's find the domain of this particular function. You realize that we cannot take the square root of a negative number. So therefore, we know that negative 2x plus 4 has to be greater than or equal to 0. It can't be less than 0. It can equal 0 because square root of 0 is 0, but it cannot be less than 0. So negative 2x plus 4 has to be greater than or equal to 0. And let's solve for this now. I'm going to subtract 4 from both sides. Negative 2x has to be greater than or equal to negative 4. Now when you have an inequality and you're dividing by a negative number, that when we divide by negative 2, that inequality has to flip to the opposite, is less than or equal to 2. So now we know our domain. Put domain here. X such that x is less than or equal to 2. X is an element of real numbers. Now for our range, if you can visualize this graph in your mind, you know that at the lowest value that x can be is 2. If I were to substitute that value here, negative 2 times 2 is negative 4. I get square root of 0. 2 times square root of 0 is 0. So when x equals negative 2, y is 3. So right away I know, since this is positive, I know that it's going upward. So actually this graph will look something like, there's a reflection in the x-axis, so this graph would look something like this. So our range is y such that y is greater than or equal to 3, and y is an element of real numbers. It's 3 because it was vertically translated. The square root function was vertically translated up. Let's now look at this function. Just going to get some scrap paper ready in case I want to explain something further because this is a little tight. Now, if we look at this reciprocal function, notice that we cannot divide by 0. So right away, we know our domain is x such that x cannot be 5. X is the element of real numbers, all right? Because we cannot divide by 5. X can be anything in the set of real numbers, but it cannot equal 5. Now, how do we get the range? There is a value y cannot be. And I'm going to propose to you the number that y cannot equal 4. And what is the reason for that? I want to show you something. If I were to sub in 4 for y, I would get this. Okay, so if I subtract 4 from both sides, I get 0 equals negative 2 over x minus 5. Now watch what happens when I multiply both sides by x minus 5 to get rid of this denominator. 0 times anything is 0. This divides out, right? And I'm left with 0 equals negative 2. This is not true. Okay, so for this reason, y cannot be 4. Let's now look at this function. What if we were to factor out that k? Well, before I go on, in number 2, what would that graph look like? Well, let's see. X cannot be 5, so let's say at x equals 5, we're going to have an asymptote. At y equals 4, here's 4, this is y, this is x, just to show you what this graph would look like. And here, we're going to have an asymptote at y equals 4, and we have an asymptote at x equals 5. Now this graph, the reciprocal function is being reflected vertically, so it's going to look like this. Approximately, it's not. I'm just doing a rough sketch so you can get an idea of what this graph would look like. So notice we have an asymptote at x equals 5. As x gets closer and closer to 5, notice that this graph will never touch x equals 5. And as y gets closer and closer to y, either it gets closer to y here, or if it gets if y gets closer and closer to 4 here or here, it will never touch the graph along the y equals x line. So that's why we say y can be anything but 4, x can be anything but 5. Let's look at this graph, this function here. If we were to factor out the k, we would get y equals negative 2, absolute value of negative 3, x plus 2, and I'm going to check my work. Negative 3x minus 6. Good. Notice the vertex of this function, this absolute value function, is negative 2, negative 4. About there. Let's say that's negative 4, this is negative 2. And because this graph is opening downwards, it's going to look like this. So this will help us get our domain in orange. For an absolute value function, any absolute value function, the domain is x such that x is an element of real numbers, and our range is going to be y such that y is less than or equal to -4. Okay, there. Function notation. Well, function notation, if you recall, is when we use f of x or f at x, and this is another way of writing y. Okay. Examples of finding f of x when given x. Well, let's see. Let's just make up a function. So f of x equals 2x squared minus 3. Well, finding f of, let's say we are given x equals 1. So what is f of 1? Okay, we're finding f of 1 given 1. So we're going to go 2 times 1 squared minus 3. 2 minus 3 is equal to -1. Okay? Now, another way we can use function notation is finding x when we're given f of x. So suppose we want to find x when f at x equals 1. So in this case, we substitute 1 for f of x, or it's like saying, well, what is x when y equals 1? It's the same thing, basically. So finding x when f of x equals 1, we just substitute. Can you answer the phone for me and tell them I'll get back to them? When f of x, 2x squared minus 3, 4 equals 2x squared. X squared equals 2. X equals plus or minus root. So, okay, so notice in this case we found f of x when x equals 1. And in this case, we're finding x given f of x. So we're doing basically the opposite of what we did up there. Did they want anything important? Sorry, August, did they need anything? Okay. Good. Sorry about that. I had a phone call, but I can't break the flow of my review. I don't have editing capabilities, so I just have to finish the review first. Okay. In this unit, you learned 1, 2, 3, 4, 5 basic functions, and I'm going to just sketch each of those rather quickly. And I'm going to do that with different colors. I'm going to make sure you bring a ruler to your exam, because that's important. X, y. Okay, the first one we're going to graph is y equals x squared. I'll do that in blue. So we'll go y equals x squared. We'll do a bullet. It's in blue. So hopefully by now you can graph these. It should be very easy for you. You need these basic functions so you know what you're doing in case you get a more complicated transformation question. That's y equals x squared. Let's draw y equals x cubed. I'll do that in red. So let's see. Y equals x cubed when 0, 0, 1, 1, 2, 8, 4, 5, 6. Well, 1, 2, 3, 4, 5, 6, 7. Oop, I'm a little bit off the graph. When x is -1, y is -1, -2, 1, 2, 3, 4, 5, 6, 7, 8. So there's y equals x cubed. Looks like that. Let's do y equals 1 over x. I'll do that in black. Okay, y equals 1 over x. There's an asymptote when x equals 0 and an asymptote when y equals 0. So let's see, the y equals 1 over x graph looks like this. Okay, here's the y equals 1 over x graph, and that looks like this. Okay, and let's see, y equals root x. I'll do that in pencil. Okay, so basically that's a v, and it will go through this way and this way. When x is negative 2, y is negative 2. Absolute value of negative 4 is positive 4. So that will look like that. Okay, and y equals absolute value of x. Let's see, what color can I do that in? Maybe I'll do it in, I've run out of colors, but I think what I'll do is I'll draw it in, oh, sorry. This should be y equals absolute value of x in pencil. Okay, and y equals root x. Y equals root x. I guess I can do that in red again. Okay, so here we go. Maybe I'll do it with dashed lines so you can see. But when y is 0, x is 0, y is 0. When x is 1, y is 1. When x is 4, 1, 2, 3, 4, y is 2. When x is 9, 5, 6, 7, 8, 9, y is 3. So there's y equals root x. You need to be familiar with those 5 basic functions. All right, let's keep going. All right, using f of x equals 2, open bracket, x minus 3, close bracket squared. You know what to do, right? Okay, good. You guys know what to do? Here's the tests if you need them. Okay, sorry, just talking to my class. They're very patient. Okay, inverse function theory. We're going to find the inverse of this algebraically. Y equals x cubed. And y equals x, it's, in other words, what I'm trying to say is it's a quadratic function. Just some theory. The inverse of a function is denoted by f minus 1x, right? Don't confuse this with 1 over f of x, right? This is just the symbol for the inverse of a function. Basically, the inverse of a function undoes what the original function does. Okay? Such that the inverse of, if the inverse of f of b equals a, then that means f of a equals b, right? Notice how if we sub in an x value into the inverse and we get a, then if we sub in a into the original function, we get b. We end up back to where we started from. Basically, to find the inverse of a function algebraically, we interchange x and y and solve for y. Okay, that's point number 1, point number 2, point number 3. And the other point I want to make, which is important, a function and its inverse are symmetric about the y equals x line. Okay? There. Some important points to remember about inverse. So as it says here in point number 3, if we want to find the inverse of this quadratic function algebraically, we're going to interchange x and y and solve for y. But first, just for to make our calculations easier, I'm going to replace f of x with y. Now I'm going to interchange x and y. Okay, and I'm going to solve for y, so that means adding 2. And then I'm going to divide by 2. Okay, and then I'm going to take the square root of both sides. So y equals, add 3 to both sides. I'm going to write it like this. Square root x x plus 2 over 2 plus 3. It should be plus or minus. Okay, I'm just going to check my work. X plus 2, divide both sides by 2, and that's plus or minus square root. Alright, or now we want to replace y with the inverse function notation. I'm going to write it like this: 1/2 x plus 2 plus 3. Okay, now let's graph both of these functions. And make sure you bring a ruler to the exam. I'm going to keep your solutions as neat and tidy as possible, so your marker, which is me, doesn't have a hard time marking. Remember, a happy marker is an easy marker. I'm not sure I should admit that over the internet, but anyway, it just helps. Okay. So, if we were to graph this, our vertex occurs at 3 minus 2. 1, 2, 3, 1, 2. Okay, we can sub in values. That would probably be easier at this point. When x is 2, y is 0. When x is 5, 5 minus 3 is 2. 2 squared is... When x is 4, 4 minus 3 is 1 squared. 2 minus 2 is 0. Now we can try when x equals 1. That will make y equal to, when x is 1, negative 2 squared is 4. 8 minus 2 is 6. 1, 2, 3, 4, 5, 6. Using symmetry, we know that there would be another point there. So this is y equals, this is our original function, f of x, which equals 2x minus 3 squared minus 2. Okay. So this is 3 minus 2. So the inverse of 3, now I want to graph the inverse. This is f of x. Now I want to graph the inverse. So we can just interchange x and y. So the inverse of this point happens at negative 2, 3. I'm going to draw it in another color. Negative 2, 3. Now this point is 2, 0. And the inverse of that happens at 0, 2. This point is 4, 0. The inverse of that happens at 0, 4. Notice I'm just interchanging. Sorry, that should be there. Ignore that point there. I'll try to white it out without making too much of a mess. Okay. Now this point is 1, 6. The inverse of this is 6, 1. 1, 2, 3, 4, 5, 6. And this point is 5, 6. The inverse of that is 6, 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So this point is 5, 6. And the inverse of that is 6, 5, right? Okay, so now I'm ready to graph this, and this looks pretty good. Okay. Uh-oh. Not used to graphing sideways. There we go. Okay, there's our inverse. It's f minus 1 of x, which equals square root of 1/2 of x plus 2 plus 3. Okay? So notice the inverses are symmetric about the y equals x line. The y equals x line is happening here. And that is a characteristic of inverse functions. Okay, determine the domain and range of f of x and its inverse. Let's do f of x first. As you know, the domain of any quadratic function is x such that x is an element of real numbers. That's our domain. Our range is, well, y is greater than or equal to negative 2. Y such that y is greater than or equal to negative 2. Y is the element of real numbers. Let's do f the inverse. Well, in the inverse, the domain of the f of x becomes the range of the inverse, and the range of f of x becomes the domain of the inverse. So we can actually just pick it off here, or you can look on your graph. Notice x is greater than or equal to negative 2, right? Domain, x such that x is greater than or equal to 2. X is an element of real numbers. Range, y, oh, here the domain was x could be anything. Here the range is y can be anything. Now, what if there's a question that says restrict the domain of f of x, so that's the original, the blue one that we drew, so that f minus 1 of x, so that its inverse is a function. Well, let's look at that. The way we do that is we look at the axis of symmetry of f of x, and we cut it in half. It's because there's two branches, and we find the two branches mean that we don't have an inverse. Our inverse function, our inverse is actually not a function. It's a relation. Our inverse relation is not a function. And so how can we restrict the domain of f of x so the inverse is a function? So let's take a look at this. Well, we use the axis of symmetry, so we could restrict f of x to x such that x is greater than or equal to 3, right? If we restrict it to x such that x is greater than or equal to 3, right? If we restrict it to this side, we want to keep that branch. then that means the inverse of that will be this, right? And you notice the pink line now is a function. Or we could have restricted it using going the other way, or we could have said x such that x is less than or equal to 3. So if we decide to keep the left side of the branch, then the inverse of the left side will be this. Okay? So it's one or the other. Okay? That's your choice. As long as you start with your axis of symmetry for f of x and pick one of the two. Uh-oh. I'm not quite complete here. I don't like what I've... This is not a complete answer, so let me fix that right now. X is an element of real numbers. I think I keep these whiteout man companies like Oops and Prit in business. And, oh, yeah, X is an element of real numbers. Okay. I wish I could ask you if you had any questions, but I can't. So you'll just have to ask me during class time. There we go. Okay, let's keep going. Let's summarize all the types of transformations that you learned in this course. Let's talk about vertical translations. So for example, when we're looking at the word vertical, if you have some function, I'm just going to symbolize it with this expression here. If c is greater than 0, f of x is translated c units up. Up c units. If c is less than 0, f of x is translated down c units. Horizontal translations. Here we're going to focus on d, y equals f of x minus d. So if d is greater than 0, we have f of x is translated d units, right? Or maybe I should say y equals f of x, y equals f of x, y equals f of x. If d is less than 0, y equals f of x is translated d units left. Okay, that's horizontal. Vertical stretches and compressions. Well, if you have y equals a f of x, if the absolute value of a is greater than 1, you get a vertical stretch by a factor of a. And if if 0 is less than the absolute value of a is less than 1, you get a vertical compression by a factor of 1 over a. Let's talk about horizontal stretches and compressions. horizontal stretches and compressions for y equals f of k x. Well, if the absolute value of k is greater than 1, you have a horizontal compression by a factor of k, and if the absolute value of k where is between 0 and 1, you have a horizontal stretch by a factor of 1 over k. Okay, now if we have a reflection about x, about x-axis, your function looks like this. And if you have a reflection about the y-axis, your function will have a negative sign, y equals f of negative x. Whew, that's quite the list, isn't it? Anyway, you have this list in your in your third unit. I just want to double check. If c is greater than 0, y equals f of x is translated up c units. If it's less than 0, y equals f of x is translated down c units. Horizontal, if d is greater than 0, y equals f of x is translated d units to the right. If d is less than 0, y equals f of x is translated d units to the left. Now with our a, absolute value of a is greater than 1, that just means if a is greater than 1 or a is less than negative 1, you get a vertical stretch by a factor of a. If the absolute value of a is between 0 and 1, you get a vertical compression by a factor of 1 over a. What does that mean? Well, if a is between negative 1 is less than a is less than 1 is another way we could have wrote that. In other words, if a is a fraction, then we get a compression by a factor of 1 over a. Horizontal compressions and stretches, y equals f of x. Absolute value of k is greater than 1. We get a horizontal compression by a factor of k. This is another way of saying k is less than negative 1 or k is greater than 1, right? This is a shortcut way of saying the same thing. We get a compression by a factor of k. I'm just double checking this because it's easy to make a boo-boo. Okay, now if 0 is less than absolute, if absolute value of k is between 0 and 1, we get a horizontal stretch by a factor of 1 over k. This is another way of saying negative 1 is less than k is less than 1, right? Or in other words, if k is between negative 1 and 1, we get a reflection about the x-axis if our a is negative, and a reflection about the y-axis if our k is negative. Good, I think we've got them all. Let's do an example. Let's graph the following function using a series of transformations. Always remember to factor your k value, which in this case is 1/2. So f of x, right? Before we do anything, we do that. Otherwise, we're not going to get the correct transformations. Equals negative 2, 1/2 times x plus 4 cubed minus 1. So 1/2 x plus 2. Good. So this is actually a horizontal translation to the left 4. All right. Now, as you know, this is a cubic function. So I'm just going to draw my axes. So again, remember to bring a ruler to your exam. Bring different colors to help you graph using by transformations. Of course, an eraser or whiteout. Okay. Now, our parent function, first we're going to graph y equals x cubed. So you should know that by now. When x is 2, y is 1, 2, 3, 4, 5, 6, 7, 8. 2 cubed is 8. Negative 1 cubed is 1. Negative 2 cubed is negative 8. 1, 2, 3, 4, 5, 6, 7, 8. So we are going using a series of transformations to graph. That's graph number 1. Now we're going to handle the reflection and the vertical stretch all in one step. Y equals negative 2x cubed. So 0 times negative 2 is 0. 1 times negative 2 is negative 2. Negative 1 times negative 2 is positive 2. So see, we're getting this reflection, and we can't graph that point, so I'm just going to draw it as best as I can. Just like that. Okay. Now we are going to get a horizontal stretch by a factor of 2. Right? When k is a fraction, we get a horizontal stretch by a factor of 1 over 1/2, which is 2. So let's stretch that horizontally. So well, the x value here is 0. Half is 0. No, it's a horizontal stretch by a factor of 2. So 2 times the x value of 0 is 0. X value here is 1. 2 times 2 times 1 is 2, so that'll be stretched there. 2, x value here is 2. 2 times 2 is 4. That will be stretched there. Okay, and then if we do the opposite side, uh-oh, I made a boo-boo. I'm stretching the wrong graph. I should be stretching graph number 2 horizontally. I'm glad I caught that. Okay, so here, x value here is 1 times 2 will end up there. That will stay there. And this will be 2. So this graph is going to look like this. That goes over 2. Over there someplace, right? This is our graph number 3. And we're stretching it horizontally. So it can end up there. Okay? So graph number 3 is y equals negative 2, 1/2 x cubed. And we can do our horizontal vertical translations. It'll be left 4, down 1. So I will do that in pencil, I guess. It's the only color I have left. So now we're translating the blue graph. Left 4, 1, 2, 3, 4, down 1. So okay, and let's see. 1, 2, 3, 4, down 1. And I'm doing the blue graph. 1, 2, 3, 4, down 1. So that looks right. And let's see, this will be going over 1, 2, 3, 4, kind of end up there. And this one will be going over 1, 2, 3, 4, kind of end up there. So the final graph looks like this. Oop! Can't touch it just yet because this is going up higher like this. This is going down like this. It'll eventually cross. I just don't think it'll cross just yet, right? It eventually crosses. It's not like it's an asymptote there, but it eventually cross the x-axis. So there's our graph number 3. Sorry, this is graph number 4, and it is our final graph. Okay, let's describe the transformations in proper order. And to get the proper order, we just follow the equation from left to right. Reflection over the x-axis, right? That negative sign we reflect over the x-axis. 2, we have a vertical stretch by a factor of 2. 3, we have a horizontal stretch by a factor of 2. 4, we have a horizontal translation. 4, 5, and we have a vertical translation. Down 1. State the domain and range. Well, that's easy for a cubic function. X can be anything and Y can be anything. Good. There we go. That's it. One more page, one more example, and then we'll have it done. Using mapping notation, recall that when we have combinations of transformations, the point xy on the graph of y equals f of x becomes the point x divided by the k value plus d, and a times the y value plus c on the graph of y equals a f of k x minus d plus c. So let's do the example we did in part 1. We're going to do this example. Y equals, I'm going to write it over here just so we have more space. Y equals negative 2 1/2 x plus 4 cubed minus 1. There. Okay. So if we want to graph this function using mapping notation, notice that k equals 1/2, d equals negative 4, right, because it's going to the left 4. A equals, I'm just following this order, negative 2, and c equals negative 1. So I'm going to do a table of values here. So x, y on, for y equals x cubed, right? We're going to transform these points, and we're going to use the mapping notation. Well, x divided by k, x divided by 1/2 is 2x, plus d, d is negative 4, so minus 4. So our x value becomes 2x minus 4, and our y value becomes negative 2y minus 1. Okay, all right? Ay minus 1 plus c, our c is negative. Okay, so On the original function, when x was negative 2, y was negative 8. When x was negative 1, y was negative 1. When x was 0, y was 0. When x was 1, y was 1. When x was 2, y was 8. Well, it is 8 on this function. Now we have to do the transform points. So negative 2 times negative 2 is negative 4. Negative 4 minus 4 is negative 8. Negative 2 times negative 8 is positive 16. 16 minus 1 is 15. So that point becomes this point under that transformation. Negative 2 minus 4 is negative 6. Negative 1 times negative 2 is 2 minus 1 is 1. 0, 0 becomes negative 4, negative 1. 1, 1 becomes, well, 2 minus 4 is negative 2. And negative 2 minus 1 is minus 3. And 4 minus 4 becomes 0. 8 times negative 2, negative 16, minus 1 is negative 17. Now we are ready to graph that. Here we have one graph, not a series of graphs. Okay, so there's y. X. Okay, let's just graph that as best as we can. Negative 8, 15. Ooh, that's right off our grid, so let's start here. Negative 6, 1. 1, 2, 3, 4, 5, 6, 1. And then we're going to have negative 4, negative 1. 1, 2, 3, 4, negative 1. And negative 2, negative 3. 1, 2, 1, 2, 3. 0, negative 17. Well, that's off our grid. And just to make sure we're doing okay here, this graph's going to look something like this. Go up there, keep going. And this graph's going to look something like this. It's going to keep going up. There we go. It looks good. I'm just comparing it to the graph we drew on the other side of the page, and I think we're good to go. You can label it. Y equals negative 2, 1 half, x plus 4, cubed minus 1. There. So work hard. If you have any questions on any of the reviews or any of your tests, please ask me during class. Take care. Good luck studying. Bye-bye.